Here are solutions to homework set number 5 for ECE 111, Introduction to ECE. In this homework set, we're looking at renewable energy. So this is a follow-on to homework set number 4, where we looked at curve fitting, specifically using curve fitting to show that the Arctic ice is melting, CO2 levels are going up, global temperatures are going up, basically kind of bad, primarily fueled by fossil fuels and global warming. Well, this homework set kind of points out that all is not lost. There is a way to produce energy without using fossil fuels, and it's cost effective. There's wind and solar, which is great for us, electrical computer engineers. But also, you don't have to listen to experts. You can analyze the data yourself. So, starting out, going on eBay last January, I found a 13 kilowatt split phase solar system that has solar panels, batteries, pretty much everything you need to set up your house for solar energy. What doesn't include is installation cost, of course. Is this a good buy? Well, using Matlab and the internet, I can download data, analyze it, and see how long would it take these panels to pay themselves off, and how much money do we get every month. So let's try it. Starting out, I'm going to go to NDON. So NDON is right here. This is a site maintained by Soil Sciences at North Dakota State University. And click on one of these. These are the weather stations. Like this is the one in Botno. It measures wind speed, wind direction, solar intensity, ground temperature, ground moisture, a bunch of other stuff. What's neat is the data is free. So if I go to NDON, click on weather data, hourly, and pick your favorite site, like Beach, North Dakota. For this problem, I want solar radiation. Pick the last 2 weeks, or pick a date range. I'm just going to pick like 2 weeks. Make sure you're in metric or SI units. If you're in English units, you're going to suffer. Export the CVS file. Open. Maybe. And here's your data. I could then take that last column, import into Matlab. And once I do that, that should be easier. It normally opens an Excel file. Must not have Excel on this computer. But anyway, grab the last column of data. That is your megajoules per square meter. And if I plot it, so take the size of my data. I have 672 data points in my data set. Your data set might vary. Depends upon the time range you pick. Let's plot hour is 1 to 672, the number of data points I have. Plot hour over 24 versus megajoules. And here's what it looks like. So this is the day. This is the solar intensity over the time range, which was September 1st to 28th, 2024 in Botno, North Dakota. Again, your data is going to vary, but you can see the sunrise, sunset, cloudy days, sunny days. That's how bright the sun was over those 28 days. Problem 2 says now convert that to kilowatts. So here the trick is convert the units, megajoules per square meter, to kilowatt hours. To do that, get the units to cancel. So I've got square meters. There's 2 square meters per panel. There are 32 panels. 1 million joules is 1 megajoule. Megajoules cancel. 1 watt hour is 3,600 joules. 1 kilowatt hour is 1,000 watt hours. 20.5% efficient. Okay, so 1 megajoule per square meter is 3.644. That's the number that I want. So take the number from NDON, multiply by 3.644, and that's how many kilowatt hours or kilowatts the panels would produce. That's the conversion factor. It depends upon which kit you buy, how many panels, the area of the panels. For this kit, the scaling factor is 3.64. If you downloaded this into English units, then you got some other conversions to do. If I then plot it, this is how much the solar panels would produce on an hourly by hourly basis. Problem number 3. Once I have that data, what is the total energy I would produce? So the top curve, this is kilowatts. The sampling rate is 1 hour. The area is width times height. Kilowatts times hours is kilowatt hours. So times 1, add them all up. This would produce 1,567 kilowatt hours over those 28 days. If electricity costs 11 cents per kilowatt hour, what it is here in Fargo, in Cass County Electric, that would be worth $172 over those 28 days. It takes Minn Kota 1.78 pounds of lignite to produce 1 kilowatt hour of electricity. That's based upon Coal Creek's data. So those panels would offset 2,700 pounds of coal in that 1 month. Pretty big number. In terms of how long it takes to pay for itself, the panels cost $11,000. I produce this much revenue in 28 days, this much revenue per year, so the panels should pay for themselves in 4.9 years, which I find kind of surprising. This is the first year that I've taught the class that solar panels actually make sense. They are less than 7 years, meaning they're actually a good investment. It would actually be longer if you don't use all the electricity you produce, longer if you include the installation costs, shorter if you include the 30% tax credits for solar panels right now. Basically right now, solar panels are actually cost-effective in Fargo, actually in Bottineau, North Dakota, even though North Dakota is not noted as being one of the most sunniest places in the world. Even here, they make sense. Plus, solar prices are dropping about 30% per year. So, yeah, it sure looks like solar's practical for a homeowner. The next set of problems look at wind energy. Again, in North Dakota, we have a lot of wind. Are wind farms profitable, or is it just all hype? Let's analyze that. Again, go to End On. When you go to End On, again, click on, slide it over. Click on your weather data, hourly, there we go. Pick your favorite spot. Let's do beach again. What I want is wind speed on average. If I do that, here's the wind speed. Make sure it's in metric, meters per second. Download that column. Throw it into Matlab. So here's the wind speed in meters per second. Plotting it. Here's what the wind looked like in the town of Bottineau between September 1st and 28th, 2024. Again, this is 2 meters off the ground. The wind turbine is actually 138 meters off the ground. To convert that to kilowatts, I need to use the power curve. So this is the power curve for a Vesta 3.45 megawatt wind turbine, wind speed in meters per second versus kilowatts. Come up with a function to approximate this. So what I'm going to do is come up with a function that plots this data and use a piecewise linear function. If the wind speed is less than 3 meters per second, output the number 0. If it's bigger than 13 meters per second, output the number 3450, and in between, do a curve fit. So here's the data. I'm going to use a cubic curve fit. Pick your favorite curve. Wind speed actually is a cubic function for energy. That's why you chose a cubic. Do least squares curve fit. There it is, least squares curve fit. Then spin through the data and check. If it's less than 3, return 0. Bigger than 13, return 3450. In between, here's your curve fit. That's the cubic function. To check it, suppose the wind went from 0 to 15 meters per second. What was the kilowatts? So this is what that looks like. The solid red line is the power curve. The dotted line is my curve fit. Seems like it matches pretty well. Okay, now that I'm happy with that, let's take the actual data at 2 meters, convert it to 135 meters. From Wikipedia, that's about a scaling factor of 1.8. Again, the wind blows stronger the higher up you get. And plot it. So this is what I expect for the output of that wind generator. Occasionally it clips. Occasionally the wind doesn't blow. What I really want is it for to clip. I want to get the full energy out of that wind turbine at any given time. If it does that, I've got a good wind site. But from this data, that's what it looks like. Let's analyze that. The total energy produced would be the integral of that, or since it's sampled every 1 hour, just the sum of it. That would produce 1.2 million kilowatt hours over those 4 weeks. In terms of pounds of coal, that would offset 2.2 million pounds of coal. Big number. That's just for one wind turbine. In terms of numbers, if it costs $4.48 million to build that wind turbine, I would get 11 cents per kilowatt hour, $137,000 over those 4 weeks. It would take 2.5 years for the wind turbine to pay for itself. That's a pretty good deal. That's part of the reason you're seeing so many wind turbines being built in North Dakota, Minnesota, South Dakota. Wind turbines are profitable. Actually, when they build a wind turbine, the farmer oftentimes get $1 million up front for the rights for the plot where the wind turbine is, plus $10,000 a year in wind rights, wind revenue. It's pretty profitable for the farmer, very profitable for the utility. So it sure looks like wind and solar actually make sense as of today. That's good news for electrical engineers. We got jobs. Also good news for the planet. So you picked a good major. Being electrical engineering is a lot of fun, and it's got other benefits too. Kind of good for the planet. So that's homework set number 5 for ECE 111.